Greetings to everyone. So today we are going to discuss about the topic of Unit 5. Okay, that is bending stresses in unsymmetrical sections. Okay. So what is the difference between normal section and unsymmetrical section? Okay. In case of symmetrical sections, the neutral axis passes through the geometrical center of the section. Okay. For example, if you are going to consider the rectangular section or square section, circular section. So this and all with respect to centroid, the section is going to be a symmetrical about both the axes. Okay. For example, if it is 500 mm, then the centroid is at 250 mm height. Similarly, if it is 400 mm, then it will be at 200 mm. So like this. Okay. But unsymmetrical section, even though if I'm considering the I section, if the dimensions are similar, then the centroid will be at its center. Also with respect to both axes. Okay, for all the sections. But in case of unsymmetrical sections such as C section or channel section, or L section, that is angular section. Okay, the centroid will be at different location. With respect to any one of the axis, it is not uniform. So with respect to the x-axis, the centroid is going to get changed here. With respect to y-axis, the centroid is going to change here. With respect to both axes, the L section centroid will be different in the both axes. So this is how our unsymmetrical section have its centroid or neutral axis position in their different geometrical section, and it is a different geometrical section, which means it does not pass through the exact geometrical center of the section. Okay, it is going to somewhere else. So hence the value of y, that is this is our y-axis and this is our x-axis. So hence the value of y for the top layer or bottom layer of the section from neutral axis will not be the same. Okay. So here with respect to y-axis or with respect to x-axis and with respect to both the axes, the centroid will not be the same. It is going to have different values. So for finding the bending stress in the beam, the bigger value of y is used. As neutral axis passes through the center of gravity of the section, hence in unsymmetrical sections, first the center of gravity is calculated in the manner of what we are going to do while doing the problem. Okay, now such that. So first we are going to calculate the value of centroid of the section. Okay, that is y bar. Okay, so either y bar or x bar, it is depend upon the section. Okay, so that is nothing but so this is the formula we are going to use. For example, if I'm going to use T section, okay, so this is one, this is section, that is the two different components, that is flange and web. So with respect to that, I'm going to calculate like this with respect to bottom. From the bottom, I'm going to. So A1 Y1 plus A2 Y2 divided by A1 plus A2. So by using this formula, I can calculate the height, that is y bar, from the centroid of the section from the bottom. So it may lie somewhere here. Okay. So this distance is nothing but y bar distance or centroidal distance. So based on nature, that is, if it is a cantilever beam, okay, so it is going to deflect like this. So in the top fiber, we can have tension and bottom fiber, we can have compression. So based on which stresses we have to calculate, based on that, we are finding a neutral axis. So here, whatever the length or whatever the height above the neutral axis, if I'm going to use, then it will become a tension stress. If I'm going to use the height below the neutral axis, means then it will give the compression stress. That is, we can have the formula M by I is equal to sigma by Y. Okay. So with respect to this sigma Y value, okay, whether if I'm going to use top fiber value or bottom fiber value, based on that I can get the tension force or tensile stress or compression stress. If it is simply supported beam, then it is going to bend like this. Okay. So here neutral axis will be somewhere here. Okay. So here top fiber have tension stress, sorry, bottom fiber have tension stress and top fiber have compression stress. Okay. So like this, it is going to bend. So if I'm going to use the YT value, then I can get compressive stress. Okay. If I'm going to use Y bottom value, then I can get tension value. So tension stress value. So based on that, we are going to use our Y value in order to get the sigma C or sigma T value. Okay. So for that YB or YT, based on the beam condition, we are going to use it. Okay. So let us move on to the problem. The first problem is a cast iron bracket subjected to bending has the cross section of I form with the unequal flanges with the unequal flanges. The dimension of the section are shown in figure. Find the position of the neutral axis and moment of inertia about the neutral axis. If the maximum bending stress, if the maximum bending moment on the section is 40 meganewton mm, determine the maximum bending stress. What is the nature of stress? What is the nature of stress? Okay, here they have given figure. One is bracket. So this is the cross section of the bracket. So I'm going to draw the diagram of I section. So with respect to this figure, it is in the little bit expanded manner. So the sizes of compression, flange, 200 mm, 50 mm, 200 mm, then 50 mm. Then thickness of web, 50 mm. Okay. So I'm going to consider this is one section, this is another section, this is another rectangular plate. So like that I'm going to consider. Now I have to calculate they have given that bending moment M is equal to 40 meganewton mm. Okay. This is nothing but 40 into 10 to the power 6 Newton mm. So this is the moment value. Now we have to find out two things. One is first with respect to the height of neutral axis from the bottom we have to calculate. Okay. So this is at yt and this is at, sorry, this is bottom and this is top with respect to neutral axis I'm telling. Okay. So first we have to calculate the yb value. So based on that, based on the value of yb and yt, we are going to calculate the remaining things. Okay. So first of all, we have to find out the centroid of this section. So this is symmetrical about the x-axis. So if I'm going to take it here, this is symmetrical about x-axis, but unsymmetrical about y-axis. So I have to calculate the y-bar value. So first, calculation of CG of the section. So section is unsymmetrical about y-axis. Okay. Therefore, y bar is equal to a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3. So here a1, a2, a3 are the distance, area of the individual plates. Okay, and y1, y2, y3 are the distance of the individual section. Okay, now that is centroidal distance of the individual section from the bottom. Okay, or from the base. So a1 is equal to, so I didn't give this one. So this dimension is 130 mm. So 130 into 50 mm. So what is the value? 6500 mm square. And y1 value is equal to, so 50 divided by 2. So which means from here to here. So this is the centroid of the first section. So what is the height? So this is 50 divided by 2. So that is 25 mm. Next A2. So A2 is 200 by 50 mm. So 200 by 50 mm. So 10,000 mm square. So y2 is equal to, so here I have first 150 mm, okay, plus this 200 divided by 2 I am going to take. So it is going to lie somewhere here, okay. So for that, so this height along with this height divided by 2, okay, that I am going to take. So 50 plus 200 divided by 2. So it is nothing but 150 mm. So next A3. So A3, that is also 200 by 50 mm. So 10,000 mm squared, and Y3. Y3 is equal to 50 plus 200 plus 50 divided by 2. Since 50 plus 200 plus somewhere here, okay. So 50 divided by 2 from the bottom. So it is nothing but 250, then 275 mm. Therefore, y bar, that is y bottom, okay, is equal to A1 6500, A into 25, then 10,000 into 150, then 10,000 into 275 divided by A1 plus A2 plus A3. So it becomes 166.51 mm. So this is the y bottom value. Therefore, y top is equal to, so total height minus this yb. So total height minus yb bar. So total height is 50 plus 200 plus 50. So 300 mm minus 166.51. So 133.49 mm is the y top value. So this is with respect to our neutral axis. So this is from bottom. Now I will mention here. So 166.51 mm. So this is 133.49 mm. Okay. So here we have calculated the neutral axis depth. Okay. Next we should move on to the formula, that is bending stress. Okay. So we know the bending equation, theory of simple bending equation, which is nothing but m by I is equal to sigma by y. So now we have the y value, no issues, but we have to calculate the moment of inertia of the entire section. So moment of inertia I is equal to, so individual section, that is individual rectangular section, I have to calculate the moment of inertia and I have to add it with respect to the neutral axis. Okay. So now let us move on to the first one. So my neutral axis is somewhere like here. So my plate is placed here. So 130 mm, 50 mm. So from the base, the neutral axis position is 166.51 mm. So I1 is equal to, okay, normal formula BD cube by 12 plus A into y bar square, okay, A into y bar square. So let us calculate the value. So B is nothing but 130 mm into D cube 50 cube divided by 12. Okay, plus area of first thing A1 Y1 bar square. Okay, so B1 D1 cube we can. So 6500 is the A1 value, Y1 bar. So with respect to this total height, the centroid is lies here. So what is the height? So this is nothing but 166.51 minus 50 divided by 2. Okay. So this height. So area into y bar square. So 166.51 minus 25, the whole square. So if I'm going to give, I can get the answer. So 130 into 50 square, 50 cube divided by 12 plus 6500 into 166.51 minus 25, the whole square. So the answer is 131.517 into 10 to the power 6 mm power 4. So this is for the value of I1. Similarly, I have to calculate the I2 and I3. So I2. So this is 2. Here I have another plate. So from the base, the neutral axis height 166.51 mm. So here we have 150 mm and the total height is 200 mm. Okay. So the centroid of this section is lies somewhere here, which is nothing but this 50 plus this 100. Okay. So this is the CG of the second section. So that with respect to y bottom to this height, what is the height? Okay. So the centroid from here to here is 100 mm. So 166.51 minus 100 plus 50, 150 mm. So this is the height of this question. So that we have to take it for as a Y2 bar. Okay. Now let us go for the I2 value. So I2 is equal to B2 D2 cube divided by 12 plus A2 into Y2 bar square. Okay. So B2 50 mm. Okay. So 50 into 200 cube divided by 12 plus A2 10,000 into Y2 bar square. That is 166.51 minus 150 mm the whole square. So 50 into 200 cube divided by 12 plus 10,000 into 16.51 the whole square. So it becomes 36 point, sorry, 36.059. 36.059 into 10 to the power 6 mm power 4. So this is the value of I2. Next I3. So I3 is nothing but the top. We have another. So 200 mm by 50 mm. So the white top is lies here. There is 133.49. Okay. So with respect to this centroid, what is the height? So 133.49 minus 50 divided by 2. This is the value of Y3 bar. So let us try with this. So B3D3 cube divided by 12 plus A3 into Y3 bar square. So 200 into 50 cube divided by 12 plus 10,000 into 133.49 minus 25 the whole square becomes I3 value. So 10,000 multiplied with 133.49 minus 25 the whole square. So 119.784 into 10 to the power 6 mm power 4. So this is the value of I3. So the value of total I, moment of inertia, I is equal to addition of I1 plus I2 plus I3 individual section. So by adding this, so 131.57, sorry, 517 into 10 to the power 6 plus 36.059 into 10 to the power 6 plus 119.784 10 to the power 6. Sorry, here I have made one mistake. So all things we have to take it from the bottom. Okay, that I made one big mistake. So if I'm going to take this, so the total from here to here, y bottom is 166.51 mm. Okay. No, this is also correct. Sorry for the confusion. So the same way we can do it, no issue. Okay, we can get the same answer even though. Okay. So now we should consider about addition of all these things. So if I'm going to add this I1, I2 and I3 value, I'm getting 287.36 into 10 to the power 6 mm power 4. This is the total I value of the given section. Okay. Now, so the maximum, for the maximum bending stress, okay, for the maximum bending stress they have asked, okay, in the given data they have asked about find the maximum bending stress, okay. So there are two values, maximum bending stress. So the formula is m by I into sigma by y. So here I need bending stress sigma, so that the formula becomes m by I into y. So there are two y values, yb and yt. So yb is 166.51 mm and yt is 133.49 mm. So among them, if I need maximum value, then I have to use maximum of these two values. So yb I can take. Okay. So I'm going to use yb here for maximum stress right now. So therefore sigma max is equal to moment value m for 40 into 10 to the power 6 Newton mm. I value is 287.36 into 10 to the power 6 multiplied with y bottom 166.51 mm. Okay. Now, if I'm going to substitute all these values, 40 10 to the power 6 divided by 2, 87.36 10 to the power 6 multiplied with 166.51. So the value of sigma, the stress is 23.177 Newton per mm squared. So this is the maximum stress. So here, whether it is compression or tension, that we have to mention. So based on the section, so the bracket have the cantilever section. So the neutral axis is somewhere lies here. So we have used YB. So I said if it is a cantilever portion, it is going to bend like this. Okay. So that compression is at bottom side, tension is at top side. We have used YB. Okay. So whatever the stress we have got now, that is the compressive stress. So this is our final answer. Okay, thank you all.